So thanks a lot for inviting me here. I'm having an exciting time at this conference. And I'm looking forward to hearing your questions at the end of my talk. The title, Full Custom Analog VLSI for Biological Inspired Computation, it's a last-minute title. Let's see if you will be satisfied after the talk with this title. So first of all, neuromorphic engineering. It's a word that has been used a lot here, and I would like to introduce the way this word was born. So in the late 80s, Carver-Mead coined the word neuromorphic, and the idea at that time was to use very large-scale integration systems and to use them in a particular regime, of which I will tell you in a minute, to mimic neurobiological architecture that we can observe in the nervous systems. And the idea was really to take inspiration from biology and put that into this kind of technology. And there's a red thing there, subthreshold analog. So that was one of the key ingredients. And I want to tell you, and I'm messing up with the instruction they gave me about the camera, so I was on the wrong side, sorry. So I want to tell you about what is subthreshold. This is a transistor. I hope many of you know what this is, but I'm gonna tell you a little bit about it anyway. So this is a 3-terminal device. You can control the current flowing through this device by applying a voltage between these 2 terminals. And that's what you see here. Here you see the transfer function, so the voltage across the 2 terminals, and here the current. Most circuits, they operate in a digital way. You have heard a lot about digital circuits so far, and what that means is that you completely ignore this transfer function. You only consider the fact that the transistor is either on here or off. So it's either 0 or 1. And then by doing that, you ignore all of this. What Carver proposed was to use this part of the transfer function, which was practically ignored at that time, and nowadays as well. There were analog circuits, but they were all operated above threshold. So if you go here, what are the advantages? First of all, you might notice that this is an exponential scale here. So with a single device, you get an exponential transfer function. As you might know, many biological processes are modeled by an exponential transfer function, and this transfer function is quite computationally expensive. The other advantage is that if you look at the current, these currents are very low, on the order of nano or picoamperes. So what you gain by doing that is also very low power consumption. Fast forward to today, as you have heard yesterday, neuromorphic engineering, neuromorphic computing as a broader meaning by it. And here I have a representative examples of systems that are out of there. Of course, it's not a complete list. And I tried to have two rows where on the top you have mostly, you have digital systems, and on the bottom you have analog systems. And so you have heard of those already, like you've heard of Spinnaker, you have heard that you can call neuromorphic as software simulated neural networks. It doesn't matter the hardware you're using for doing it. You could use a GPU, you could use a CPU, but you could use also a supercomputer. Then you have heard about IBM through Nord, and the first day we focus on learning about Lohi from Intel. There are other systems down here that are analog. So for example, the BrainScales, Brainstorm from Stanford, the Dynapse system from Zurich, and you have heard of systems that can be based on memory stores. As I said, this is not a complete list, and I'm not going to the details. Different you can see in these different systems are, for example, is the system operating in real time or accelerated time? Is the system able to do learning or not? Things like that that might affect your pick, you know, which one is your favorite. It really depends what you're trying to do, what are the features that are important for you. And just a short note, like, you know, if you stay in these systems here, these two might be the representative for the Carver-Mead kind of approach, the analog subthreshold. So let me give you a few motivation about why I've been doing this the whole way. Why do I get through the pain of doing full custom VLSI? And I'm not going to give you the answer immediately, but I'm telling you that I'm going to focus on two topics today. One is learning, and one is closed-loop specialized system. So I believe that this kind of systems can have an impact on these two research fields. And I really like the example we had from Tom yesterday, where he was showing the difference between machine learning and biological learning, and there was the race with the car and the motorbike, and he said, yeah, you cannot put the car on the motorbike. So there are some things in which, if you do it biologically, you are on the motorbike, and you don't need a big computer, for example. And these two examples are going that direction, but I'll give you more detail during the talk. And here, one thing you could focus in terms of learning is, if you want to do online lifelong learning, this is very different from machine learning today. So if you want to keep on learning through your whole life without somebody telling you what is this and what is that, this is a way to go to look at biological system. And the other one is really looking at small biological systems that evolved to optimize some feature so that they can solve a task particularly well with very limited resources. So if you're able to copy those, then you're going to have very efficient system in small devices that operate at low power. So let's start with learning. By the way, I come from basic research, so mostly I'm interested in understanding the brain, and then application is a side effect of it. So how do I get along with understanding learning in the brain? As a physicist, I get inspiration from this sentence that was written on Feynman board, which says, what I cannot create, I do not understand. And now the first question is, how do we create learning in an artificial system? And what people have been doing is, yes, Tom, I have the comparison, brain versus computer, which you predicted all of us are going to have, and I didn't remove it. So how are people doing learning, even if it's inspired by biological systems? They use computers. So the most common approach is to use computer. And this graph from IBM is very useful to tell you one difference between the brain and the computer. So here you see clock frequency, and here you have power density. And here you see processors, how they develop over the year. And as it is clearly understandable, processors have been going toward as much as possible higher frequencies, and that brings also power density. Where is the brain in this graph? The brain is here. You can argue on the exact number. I don't believe this is a good estimate, but I don't believe we can have a precise estimate of this. But this is telling you that the operation is at completely different scale. And so this is one fundamental difference that we have to consider, that maybe we are not using the right substrate for implementing those principles when we use computers. And there is another important difference that was mentioned already, which is the von Neumann bottleneck. And this is what you see here, represented in this block diagram. Memory is here, computation is here. This is very particular of computing systems, but this is not what you see in the brain. So in the brain, memory and computation are co-localized, and that might make a huge difference in the way you can implement learning. So already in the late 70s, John Backus was mentioning that programming is basically planning and detailing enormous traffic of words through the von Neumann bottleneck. And much of that traffic concerns not significant data itself, but where to find it. So in computers, we spend most of the time moving data around. And even worse, if you look at how the velocity, so how the bandwidth of this bus for the memory is evolving over time, and if you compare it with how fast CPU are improving, that's the graph you see here. So this is now the development of CPU speed against memory bandwidth over the last 25 years. And you see that this is here. My pointer stopped working. This is here an exponential scale. This is the 25 years. And you see this line, which is a good fit of the data. What that means is that the imbalance between CPU and memory transfer speed has been growing exponentially. So when you want to simulate learning, this is, of course, a really big problem, because by doing learning, you need all the time to read the value of the synaptic weight, update it, and then write it back to memory. And as I said, computation is going to be very fast, but you're going to spend all the time doing the read and write. So let's go back to biology, and I want to talk a little bit about associative neural network, or also called attractor neural network. And this is the motivation from biology. So this is results from very old experiments in 1988. Miyashita and Chang then were working with behaving monkeys, and they were looking at activity in the infratemporal cortex to figure out how we can store memories in our brain. And basically, the monkeys were shown these kind of very abstract images, and they were trained to do a delayed match to sample task. That means they were shown one image. After a delay, they were shown a second image, and they were supposed to say, yeah, these two images are the same or not. And that's a graph that describes this kind of protocol. Forget about the details, but here you have the first image presented, and here you have the second image presented. And in between, the monkey would see no image at all. So the monkey was supposed to remember the image. And once the monkey was trained enough and then learned to recognize this image, what they could observe in the infratemporal cortex was that there were neurons that during this delay period, they kept the activity high. So these neurons became selective to some of the images, and they were able to keep the memory. So this so-called delay activity or sustained activity of those neurons is what was believed to be the memory of the image that was shown in this time, but not during the interval here. And then, of course, the same neuron would not respond to other images, so they were selective to images. And so from this, you can think about all the theoretical development in attractor neural network, Hebbian learning, and so on, where the idea is that you have an ensemble of neurons, so here, which is stimulated by an input. And this input is going to activate a subset of neurons in this ensemble, in this case, the gray neurons. And if you have a form of learning that is encouraging coherent activation of neurons, what you will see after a while is that connections among these neurons will become stronger, and that's the black lines between those neurons. So what you see is that at the very beginning, when the network is in this state, if you present the stimulus is going to make an increase, provoke an increase in the frequency response of the gray neuron, but this increase is going to go back to zero after the stimulus is removed. But once this kind of attractor are formed, what you see is exactly what was observed in biology. The stimulus produces now a higher activation of those neurons, and after stimulus removal, activation stays there. And so this is now, again, a memory that you can implement in these networks. And now the question is, of course, how do you do the learning? How do you make this synapse learn the co-activation of neurons? And again, I'm going to look back at biology, and basically there are two important mechanisms that have been observed. And one is related to mean firing rate, and the other one is related to the exact timing of spikes. And you have heard of the second one, Stdp already. This is a representation of the first one. So this is, again, biological measurements in which one is looking at a synapse, and the synapse is stimulated here with a pulse, and then the effect of this pulse is observed on the postsynaptic membrane potential. So what you see here is how the neuron react to this impulse input. And then after you measure this, what you do is that you do a stimulation of this synapse at high frequency. And that's what you see here. In this case, you don't even measure, but you measure afterward. And what you observe is that the effect of the single event here is augmented because the synapse became stronger. And that's what you see here. You do this kind of measurements here many times so that you can measure the baseline, the starting point of your synapse. And then if you do this kind of measurements later on, you see that there is some transient here, but then the synapse stabilized to to a strength which is higher than the initial one. Stdp, as I said, I don't have to say much. It has been discussed already a lot. You have two neurons. The timing of pre- and postsynaptic spike matters. When the presynaptic spikes arrive shortly before the post, you have potentiation of the synapse, and that's what you see here in a positive change of the weight. You have a negative change of the weight where the post is likely before the pre. So following these two biological observations, many models have been proposed. And following the computational neuroscience community that was proposing these models, also the neuromorphic engineering community proposed circuits for implementing these kind of models on analog VLSI. And these two figures are representative, again, of the two kind of observation, the mean firing rate and the Stdp. Those are two figures from two papers that did implement these models on hardware. And the models on mean firing rate have been mostly based on a model proposed by Stefano Fusi, now at Columbia. And the idea is that you look at presynaptic spikes. Whenever you have a presynaptic spike, you do an update of your synaptic weight here, and the update depends on the state of the postsynaptic membrane potential. And then later on, the rule evolved to be a bit more complex to accommodate more of the biological features, but the basic concept is this one, and by doing this, you get mean firing rate kind of learning. This is also compatible with Stdp, if you think, or we can discuss about it later, but it's not explicitly implementing Stdp. Then the other approach is really measuring the delta T and inducing changes in the synaptic weight that are driven by this delta T. And I have a very short representative list of work that have been following this approach with a short description of what people have been demonstrating then with this hardware. Things like learning activation patterns in a recurrent neural network, or pattern recognition of 2D binary images, attractor dynamics, learning spatiotemporal patterns, supervised learning of classes, unsupervised learning of. This is from the mean firing rate side. And on the Stdp side, you see things like synchrony detection and amplification, Hebbian learning supported by Stdp, order classification, and Stdp learning on floating synapses. I have no time to go into the details, but I'll be happy to answer questions later on if there are. Okay, now let's go to my recent work. My dream is to come up with a general theory of learning. And this dream is also motivated by the struggle of doing analog VLSI. You might be aware of the fact that when I do a full custom chip, I have to decide what model I'm going to use. And then I'll be stuck with that model as long as possible, because making a new chip is expensive in terms of work and money and other things. So I got inspired by this work by the group of Nicolas Brunel, where they propose a model based on calcium that has the promise of merging the two things, the mean firing rate approach and Stdp. And how does it work? It's, again, a local rule. It looks at pre- and postsynaptic activation. It computes a calcium variable out of this pre- and postsynaptic activation. And they show that by updating the synaptic weight, depending on where this calcium activation is, you can get all kind of learning. So first of all, Stdp, you have seen so far the classical shape, so which is, again, here. So you get potentiation for pre before post and depression for post before pre. But in biology, several kinds of Stdp shapes have been observed, and that's what you see here, a plethora of different Stdp kind of learning rules that this model is able to reproduce. More interesting, when you look at Stdp in biology and you look at the biological data, what you should pay attention is that the frequency of stimulation in these experiments is very low. So the Stdp plays a crucial role when you're stimulated at 1, 2, 3 Hertz. So that the delta T is very significant compared to the interspike interval, which is much longer. But of course, you can imagine that if you go up with the frequency of the stimulation, at some point, biology is not able to care anymore about the precise delta t. So what you observe in biology is that if you repeat the Stdp protocol by changing the frequency of the pairs, you will eventually see only potentiation, no matter what. So even if the delta t is compatible with depression, in the synapse you're looking at, as you increase the frequency, you will see only potentiation. And that is what this model reproduces, and this is shown in this graph. So at low frequency, now the black is 1 Hz. You see the classical Stdp. As you increase the frequency, you go to red, green, blue, and yellow. And yellow is going to be 50 Hz. And so as I just told you, in biology and in this model, when you go to this kind of frequency, you see potentiation only also when the delta t would be compatible with depression in the classical Stdp. So because of all this reason, we went through the effort of putting this on silicon. And I'm not going to go to the details of the circuit because it would take too much. But basically, the circuit is composed of 3 blocks. One is for calculating the calcium dynamic. One is for computing the dynamic of the synaptic weight. And one is for the bistability. What I didn't mention so far is that in this model in silicon, we normally store the synaptic weight on a capacitor. So a very effective way of keeping the memory is to reduce long-term synaptic weight into 2 stable states. And so that's why we need a block here to implement this bistability. And this is data from a silicon chip implementing this kind of model. And this is just to show you that we can reproduce the observation on the model on silicon. So these are 2 representative examples. Here you see the classical Stdp. So negative change in weight for pos before pre and positive change in weight for pre before pos. And here you see the frequency dependency. So in this inset here, we focus on this particular delta t. So it is a delta t that gives you depression. But if you increase the frequency of stimulation that is here on the x-axis, you will see that at some point the change of weight will cross the 0 and become positive, therefore reproducing this kind of result here. And as for the model, you can change the shape of the Stdp dynamic, and still this property about the frequency will be conserved. So let's go back to the attractors. Now we are putting these circuits in CMOS VLSI. We're using subthreshold. You might know that we are affected by noise. And what I call quench noise in this slide is the fact that there are fluctuations in the properties of the silicon on which we put our CMOS circuits. And because of that, 2 synapses that are in principle identical are not going to be identical on the chip. So we have to pay attention to the effect of this kind of noise, which is something that is useful also for the memory store community, where you have similar problems. Maybe until now, the percentage of variation is still much bigger. So we investigated the robustness of an attractor neural network against this noise. And here we use really the variability that we observe in the chip. In this case, is a Monte Carlo simulation of device mismatch on the chip that we designed. And we look at how this noise affects performances of Attractor. So what we did, and this is unpublished data by a master's student in my lab who just finished. And what she did, she identified 3 kinds of responses of the network after the stimulus is removed. So the first one is no delay activity. This is what you see at the very beginning. You remove the stimulus, delay activity is gone. The second one is fading delay activity. So you have delay activity for a while, but then it dies off. Or you have stable delay activity. And this is experiment on 50 networks. Every time you randomly initialize the network by having random connections among neurons. And then what you see here is that if your stimulation is too short, here she was using a stimulus of 1 second duration, If it's too short, you don't, the learning is not fast enough. So in 1 second, you don't potentiate enough synapses, so you don't have delayed activity. But if you do for 2, 3, 4, or 5 seconds, you see that you have either fading activity or delay activity. And in a network without noise, the more you stimulate, the more you improve your performance, the more stable delay activity you get. And if you add noise to it, you see that at the beginning it's quite similar, but the problem is that you don't improve. But there are many parameters that are used in this network. And here you could imagine that the maximum synaptic rate allowed is not enough, even for the network without noise. So you could think, okay, I don't want to operate the network anyway in this regime. I want a stronger weight so that I'm able to have stable attractor. And the good news is that when I do that, the noise doesn't have a destructive effect anymore. And that's what you see here. So if I set the maximum synaptic weight in the network high enough so that the network without noise is stable, and even after 1 second gives me stable attractors all the time, this is what I'm gonna see in the network with noise as well. So this is the good news, that we can find the good parameter set to make sure that the noise is not destructive. And I have to keep an eye on time, but this is now a short break concluding this first part of the talk. And talking about the vision, you know, what is my vision on doing learning in this kind of way? And I think neuromorphic engineering done in this way, and I repeat it, it's this analog subthreshold VLSI, has the potential for embedding unsupervised online lifelong learning into artificial systems, therefore making a crucial contribution towards the realization of fully autonomous systems. And just to give you a bit more of details of what I mean about that, here is somehow a list of ingredients. So I'm talking about online lifelong learning. What do you need for that? For example, again, if you look at machine learning, you're given your training set, you do the training, and then you use your network. This is not the way we operate. We learn all the time, and an associative network give you the power of learning basically the statistics of what you see. So, and this is very powerful if you do slow learning, because it gives you also high memory capacity. So basically, if you walk around and you keep on seeing things, you will not learn something that you see once, because this is probably not important. But you will slowly learn something that you keep on seeing. And by doing that, you make sure that your memory span is big enough. And then when it's saturated, the network is not going to collapse. What is going to happen is that you are going to forget the whole things that you haven't seen for a long time, and you're going to make space for new memory. Why analog VLSI? Because, as I said, you're going to hit the memory wall when you do this. So this network, these synaptic dynamics are so complex that you will have to work computationally on updating the synaptic weight all the time. And if you do it in analog VLSI, you're guaranteed that it's going to be always fully parallel. And so you gain with that. Of course, memory state device is one alternative that is coming up in the last years. Local learning rule, I mentioned it a few times. It was mentioned during the Lohi workshop. So in Lohi, they also took care of making sure that the learning rule is local. And I think this is important whenever you have a physical system. So whenever you have a physical system, you need to keep the learning rule local. Of course, if you write a simulation, you can always say, okay, I take all the synaptic weight of the network and I rescale all of them for a factor, just to do, for example, homeostasis. But the brain, as Lohi, as analog VLSI, would not be able to do that, because the computation is happening local, and it can only be done on information that is available locally. So now let's move to the next topic, and I need some water. By the way, I didn't say it, but interrupt me at any time if there's anything you want to be clarified. So a completely different topic. And I'm gonna start again from comparing biology and technology. And this time in vision, but vision is only one example. You can make it more general than that. So clock-driven sensing, think about vision. You have a camera, you have frames. You're going to acquire images at a specific time, which is not driven by the signal itself. So here you have an example in which you are trying to monitor a certain signal here, and you do it in a frame-based way. So at every clock, you acquire a full frame, no matter what. So what you end up having is redundancy in some cases, because imagine nothing is changing in your visual field. You're going to get data over and over again, and the data is the same. It doesn't change. You're also going to lose information when the changes of the signal are faster than your clock. What about biology? What you see in biology is that you have event-driven sensing, and what's driven the sensing is changes in the quantity that you're measuring. And that's what you see here. The effect is that when there is no change, you don't get redundancy. So you acquire here, but then there is no change and you don't acquire anymore. And you know that your latest data is still representative of the signal you're measuring. Thanks to this, you have another advantage here. I put only one word. Instead, here I have many words. The thing is that by doing this, you can do it locally. So you can look at the single pixel and acquire only the single pixel while the luminance at that pixel is changing. So again, you gain data, because if only one pixel is changing, you don't have to get the full frame. You also get fast sensing, because now the sensing is driven by the changes. So if the changes are fast, you're going to sample faster. And this is a nice illustration on what happens when you do that. This is from the Davis Silicon Retina by Toby Delbrook. And this is just when you move in a street, what you would see with a sensor like that. And you have black pixel and white pixels, and they represent negative and positive change of luminance. So basically, if you walk around or if you drive around, you're going to see edges of the objects that are in your environment, and they're going to move in your visual field. So I'm talking about how event-based visual sensing and self-motion act together. And then what do you get from this kind of signal? You can get information about distances of objects in your environment. So you all had the experience of sitting on a train or on a bus, and the trees nearby is going to move very fast compared to the house far away. So if you get information about motion, you can get information about distance of objects. And you can use this information for navigating into the environment without jumping into objects. And basically, what we have done is look at how the bee does that. So in collaboration with Professor Martin Egelaf in my university, working on flight control of bees. And we are putting together a model for obstacle avoidance, and later on we'll put more complex feature for navigation in it. But today I'm going to present really the first steps we have done in this direction. And the first thing we have done is that, okay, we want to use this kind of sensors because of what I said before, because it's very efficient. We get really the data that we need for our task and nothing more. And so we have spikes. And the classical elementary motion detector model that you might be aware, it's really looking at how you see response in the insect eye that code motion. And we made a modification of this model to make it compatible with the spiking input that we had, but also to empower it with a richer behavior. And that's what I want to explain you here. So this is a block diagram telling you how the model works. So you're looking at 2 pixels, and basically you want to measure the time to travel of an object that is moving from one pixel to the other. And that's what you see when you're moving the tree passing by, for example. And so the moving object is, in this case, represented by 2 spikes. So it arrives to the first pixel at this time, and then it arrives to the second pixel at this time. What we do is that when the first spike arrives, we sample the time by accumulated charge on a capacitor, and then we let it decay over time, and that's what you see here. Now, when the second pulse arrives, we sample the value of this decaying voltage, and we use it as a multiplication factor of a synaptic weight. So here we have a synapse, and the weight of this synapse, which is receiving this spike at the input, is modulated by this value here. What does this give you? This is shown here. Now, the first example is just telling you that this thing is direction selective. If you get these two spikes in the wrong order, is of course not going to work, and that's what you see here, because you get the spike on the second pixel first. So the first pixel is not excited yet, and so the blue curve here is representing this sampling. This is not there yet. When the first spike comes, so the multiplication factor is 0. So if you look at the postsynaptic membrane potential, you see nothing. There is no current getting into the soma. But now, if you get the right order, you get the first spike, and then after a short time, you get the second spike. And now, in orange, you see the synaptic current that is going to be sent to the neuron. And this synaptic current is calculated by using this value as a multiplication factor of the blue line, which is the decay from the first pulse. And then if you look at the postsynaptic membrane potential, you see that a lot of current is going to be provided to the neuron, and because of that, you elicit a lot of spikes, and then after a while, the neuron relaxes back. And of course, the delta t plays a crucial role. You have an intrinsic time constant, which is decided by the blue curve here. And so if the second spike arrives too late, you still have a multiplication factor. You see a small current here. This is going to elicit some response in the neuron, but this response is below threshold. So good so far. What do you get out of it? First of all, we want to put it on silicon. This is now a circuit, but I'm not going to go into detail. This is just to show you that we did this exercise, and we have everything on silicon, and we have 3 blocks that are now, again, shown here, a block for doing the sampling, a block for doing the synaptic connection, where an input comes from the sampling to modulate the synaptic strength, and the output current of the synapse goes to the neuron. And then what do you get? You get on silicon the same kind of behavior that I showed you on simulation. So here you have the example of a very short delta t. These are oscilloscope traces taken from the silicon. Here you have a short delta t, and you see the postsynaptic response giving you a lot of spikes. If the delta t is longer, you get less spikes. Of course, then we characterize this on silicon, and here you have the response of 8 SEMD, spiking elementary motion detector, as a function of the delta t of the 2 spikes. And here again, something I mentioned before, there is device mismatch, so every neuron is behaving slightly different than the other one. And I have to say this was somehow bad layout design, and it can be improved. But we don't want to make it perfect anyway, and we can discuss why. So you get spike count now that is telling you how fast is the object moving. So it gives you an information of motion. Interesting enough, you get this information in the exact timing, and that's something we didn't think when we designed the model, but later on, by doing measurements on the chip, we realized, okay, let's look at the interspike interval. So we have a burst of spikes that are within 10 milliseconds, but we have single spikes in them. So why wait until the end and count them? Let's look at the first 2, for example. And that's what you see here. So every curve represents a different stimulus with a different delta t. And this is the response of the spiking EMD from the silicon. And now you look at the first 2 spikes, so the first interspike interval, and you can already say, okay, this is a very fast stimulus or a slow stimulus. But of course, you don't have enough resolution to distinguish the fast-moving objects. But interesting enough, if you go on, I mean, you know that at the end you'll get this information because the spike count tells you that. But you can see that over time, if you look at more and more interspike interval, eventually you're able to separate the fast velocity as well. So this is now a very interesting coding scheme in which you can achieve very low latencies, because if you can make a decision on 2 spikes that are here, the interspike interval is 0.5 milliseconds. So you can make an immediate decision and then probably adjust it later when the resolution gets higher. So how we use this kind of information to set up a neural network that can do obstacle avoidance with it. That's shown here. So first of all, what we do is we apply this kind of computation all over the visual field. So here you have a representative location, but this is done everywhere. And then what we do, because at the moment we are not flying yet. In the future, we would like to fly, but on the moment, we are moving on a flat surface, so we don't care much about elevation. We just collapse every column together. And then, okay, now here I have spikes that are telling me how much motion there is in this column. And what I want to do is avoid directions in which there is a lot of motion. So what we did is a so-called winner-take-all network, but we inverted it because the input is excitatory, so we want the network to select the orientation with less motion. So that's why we provide a baseline activation here, and then we inhibit with the output of the SEMD, and then the final outcome you will have is that only the winner will select the location with the lowest motion. And then, of course, you can use the output of this kind of network to drive a robot around and make sure that this robot doesn't fall objects. And that's what we have done. Here we've used the EDVS camera by Innovation and the Spinnaker hardware to fast prototype our ideas. As I told you, it's a struggle to do analog VLSI because the time frame is much longer, but luckily nowadays we have a lot of tools that we can use to really test our ideas quickly and then to decide to go on with the hardware. So we put everything on Spinnaker, we put it on a wheeled robot, and this is also unpublished work from another very good master student in my group that set up all of this, put it on a robot, and then did very simple experiment in which this is the trajectory of the robot, and it was measuring it while the robot was confronted with an obstacle. There is noise in the system. The noise is given by the baseline. The baseline are Poisson spike trains. So as you can see, the network is going to randomly select either right or left direction depending on this noise, but it's effectively avoiding the obstacle. The same here, we have a corridor made of poles, and the robot is able to navigate inside this corridor without jumping into the walls. And of course, as soon as this is the point where the poles are not anymore visible to the robot, so at this point, the robot starts getting random directions. Of course, the next step here is to introduce a goal direction. At this time, the robot doesn't know where it wants to go, but later on, we'll introduce the goal direction as well. So I think I'm doing well with time. Let's look at the vision again. This is an example, but the vision that is represented by this example is really that nature evolved optimal solution for demanding sensory action control loops. And this was done when animals were, for example, small and had very limited resources. So the bee is a fantastic example because the bee does amazing things, and it has 1 million neurons, and it's very small, and it runs on very low end. So I think that's where we can learn something, and we can port the neural substrate of these animals into artificial system. And by doing that, we're not going to have general purpose computation. We're going to make a system that solves one particular task, but it does it particularly well given the limitation of the resources. And I would like to conclude with this. I have to put up my acknowledgement slides, and I hope I convince you that there is a motivation for keeping up the tradition. Of course, this motivation has very specific application, but I'm really excited about those applications. Thank you for your attention. Questions? Yes?
So, last thing you were talking.
Yes.
Local.
Yeah. Yes, of course.
You overload them.
Yeah. So first of all, this computational element is much more general than what I told you. We are applying to vision, but there's nothing in it that has a constraint in vision. So we are also already investigating, for example, audition. You can think even to apply it to touch, for example, artificial touch when you do it event-based. And it's fully open how you connect it. So there is no constraint. In this case, we did it locally because for the task we were looking at, we needed it to do locally. By the way, we don't do it pixel by pixel. As you might be aware of, there is noise in this kind of sensor. So we already do some spatial temporal filtering before going to the SEMD. So we have like a 3x3 pixel block with a time constant of integration, and then the output of this block is sent to the SEMD. But of course, if you're interested in long distance motion and that kind of things, you can just plug this module in a different way. That's completely open. Yes?
It's not like a question, it's more clarification for me as I'm new to this topics. Like, so you mentioned the mean firing theory and like attractor dynamics. So are all this the same? Like I read also the rate model theory, the recurrent networks. So this seems different branch than the spiking neurons, right? Like, so what's the advantage, disadvantage between those, like the mean firing theory and the kind of typical spiking neuron models, you know, if that makes sense?
Yeah, so I didn't have time to go into the detail. There is a huge theory behind this. And mean field theory, you're right, it's in the mean firing rate, but it has been proven that you can translate it to spiking neural net. And by doing analog VLSI, I see a lot of advantages in having spikes. So the spikes give you the advantage, for example, of transmissions of data, which would be very expensive because if you model mean firing rate on an analog circuit, you're going to have a voltage that it's very expensive to send around. So it's not practical. At the same time, I'm really interested in how the brain does it, and the brain does it with spikes. So any model that fails the spiking implementation, to me, fails explaining how the brain does it. That doesn't mean that the spiking one gives you the guarantee, but at least you proved that by using the same kind of substrate, the model can do what it's supposed to do.
More abstract level from the spiking, like it's more kind of...
It's more abstract level. It helps you a lot in defining the right parameters, for example. So what I show you about the stable attractor, you have so many parameters in this kind of network, and mean field theory helps you figuring out what are the right one to get the attractor stable, for example. And then you can couple the two things together.
Thanks a lot. Really, really exciting talk. I'm just interested in one thing you said in the first part of the talk. You said we don't use something, then we forget, right? Like, you know, if it is the network is too much loaded, then you will keep on forgetting what we did first, and you know the way. I would like your comment on say I was 5 years old. I'm just making up things, right? And I had this glass, and I remember glass falling and it breaks. And then for next 50 years, I never saw a glass or it falling and breaking.
Yeah.
Now somebody comes back to me in 50 years and tell me, you know, when the glass, if you make it fall, it breaks. Now when he tells me that, you know, just an example, but it relates to many things that we experience in life. We say, yeah, exactly. You know, so my question is, this recollection of this glass falling and breaking, is it a biological recollection or a more psychological recollection? What I'm trying to ask is, was this information actually stored somewhere in the brain, which we reconnected, or it is not?
Yeah, so my statement wasn't so strict as you probably have experienced it. I made it because originally there were networks proposed where the memory capacity was limited, and this is the case also here. But the problem was that if you exceeded this memory capacity, the next thing you wanted to learn would totally disrupt network operation. So you would fail to remember anything. So that's what we have here instead is the so-called palimpsest property. And that's what I mentioned, that you make space for new memory by deleting old ones. This doesn't explain everything in biology, you're right. There are memories that you make when you are very young and you keep for life. There are concepts as one-shot learning. It was mentioned yesterday, pain. You touch something, it's painful, you're gonna remember it. You don't need to try it again. So there are different mechanisms in biology. I think, many models, they are looking at some aspects, but they cannot explain everything. And there are other mechanisms for which you have memories, such the one you mentioned, that you acquire as a very young child and you keep forever. But there are also things that you forget. And in some cases, it's useful to forget to make sure you can learn new stuff.